Hello and welcome to the fifth part of Lesson 4. In the last video, we developed a four-step protocol to help us simplify and solve the Navier-Stokes equations. What I think would be really helpful now are some examples of applying this protocol. So, in this video, we're going to examine the flow of a viscous liquid in an infinitely wide rectangular slit. Now, this sounds like quite an abstract example, but the solution that we'll develop allows us to understand how to apply the Navier-Stokes equations to flows that are relevant to engineering problems. So, here on the blackboard, I'm going to draw a diagram. The diagram will be very familiar because it is one of the flow scenarios that we looked at in the last part of this lesson. I'm in a Cartesian coordinate space. I've got an infinitely wide slit that is parallel, and so into the screen there's infinite depth. So, what I'm going to say is this is a pressure-driven flow, just as we did in the last part of this lesson, and that I have a high pressure, P1, on the left-hand side, pushing fluid through this rectangular slit to a lower pressure, P0, on the right-hand side. Now, I said in the last part of this lesson that the flow profile will be parabolic across the slit. We're going to prove that now in this part of this lesson. Now, let's solidify the problem somewhat and identify some physical properties. So we're going to assume that the fluid in this gap has a density of 1,000 kilos per cubic meter. We're going to furthermore assume that the viscosity is quite high. It's like honey that's been put in the fridge, maybe honey that's been put in the freezer, and the viscosity is 100 pascals second. So it's very, very thick fluid. We're going to assume the flow is fully established. That means the flow is at steady state and doesn't vary with time. And I'm going to say the gap between the top plate and the bottom plate is actually really small. It's about 2 millimeters. So, there on the blackboard are the Navier-Stokes equations. Now remember, step 1 of our workflow involved justifying setting that substantive derivative to 0. So that's what we're going to do now. We're going to justify this in two ways. Firstly, we're going to look at the level of inertia in this flow. We can work out the Reynolds number in terms of the flow velocity, because the only thing that we don't know in the Reynolds number is the flow velocity, and we can work out that the Reynolds number will be 0.02 times v. Now, if v is even of order a meter a second, which is a very fast flow for a gap that's only 2 millimeters wide, we can see that the Reynolds number will be 0.02. There is not a lot of inertia in this flow. So that would be one justification we can use to ignore the substantive derivative. There's a far better justification for this particular example, though. It's because if we look at our geometry, and if we look how the fluid is flowing from pressure P1 to pressure P0, the geometry doesn't change. And we've already stated that the flow is fully established. So therefore there is no acceleration in this flow, either temporal acceleration or spatial acceleration. So there we have two justifications as to why we can set that substantive derivative to 0, and we only need one justification to do that. So what we end up with at the end of step 1 is that 0 is equal to Fg minus grad pli plus mu del squared v. Okay, let's take the second step. The second step, if you recall, was to identify the dominant flow direction. We've got on our sketch here, and I thoroughly recommend you do sketch the problem out to help you identify where the flow is going and where the pressure is changing. Our only flow velocity is in the x direction, from left to right, from high pressure to low pressure. If we consider how the x direction velocity changes, it's only across the gap. At the bottom of the gap, the fluid stuck to the wall. At the top of the gap, the fluid stuck to the wall. We call those no-slip boundary conditions. In the middle of the gap, the fluid's flowing. It doesn't see the wall effect. So the x direction velocity only varies as a function of y direction. If we consider the dominant pressure variation, we're going from a pressure P1 at the start of the slit to a pressure P0 at the end of the slit. So the pressure only changes from left to right. The pressure only changes in the x direction. Our streamlines are straight and parallel. And remember, if we were to have a transverse pressure gradient, we'd expect streamline curvature, and there'd be a pressure gradient at 90 degrees to that curvature. These streamlines are straight. There's no curvature. There's no pressure gradient across the width of this gap. We're also going to stick with our Cartesian coordinate system. because we've got a rectangular geometry that's easily described by a change in x, a change in y, and a change in z, where the z direction is into the blackboard. So that is step 2 complete. Step 3, we're now going to apply those simplifications or those observations to simplify Navier-Stokes equations. So the first simplification we're going to say is, look, this flow is horizontal. The only velocity component that exists is in the x direction. If gravity were to be there and have influence on the flow, there would be flow in the y direction. There isn't any flow in the y direction. We can neglect gravity. We can neglect the body force term, which simply leaves us with pressure variation and velocity variation. Let's look at the pressure variation. We've said that the dominant pressure gradient, the only pressure gradient, is in the x direction. So the only non-zero term of grad p is dp by dx. Let's now think about velocity variation. We've already identified that the velocity is in the x direction and it only changes in the y direction. So the only non-zero term of the Laplacian is going to be d2vx by dy squared. And so we can simply write at the end of step 3 that dp by dx, which we're going to approximate to being p1 minus p0 divided by the distance between them, L, is equal to the viscosity mu times d2vx by dy squared. Fourth step was to identify boundary conditions. Now, we can make the boundary conditions easy to implement if we're cunning where we place our coordinate axis. If we look at our flow that we've sketched out, we've identified that the flow is symmetric. It's symmetric around its centre line. The centre line is also the point where the velocity is at maximum. I'm going to elect to place my coordinate system such that the x-axis lies on the centre line. Now, we could place the axes anywhere and the result would be the same. You just require a little more algebra to get there. We'll see in a minute that by placing the coordinate axes on the centre line allows us to evaluate boundary conditions very, very easily. So, at the centre line, I have zero velocity gradient, dvx by dy equals 0 at y equals 0. Moreover, we know that the fluid is stuck to the upper and the lower wall, and those upper and lower walls aren't moving. So we know that my x direction velocity is 0 at y equals plus or minus h. And I've said h is the distance between the centre line and either the top or the bottom of the gap. So that is step 4 complete. So now, with this information, let's solve this second order ordinary differential equation. So, the first integration step involves simply integrating that pressure gradient with respect to y with how we integrate that second derivative on the right hand side. Now, I've written that second derivative as d by dy of dvx by dy. That is essentially the same statement as d2vx by dy squared. It just makes the integration a little more obvious, because if we look at the right hand side of that integration, the integral that I'm going to end up with is going to be dvx by dy. So let's take that step. The left hand side I'm going to integrate with respect to dy, and that gives me delta p over mu L, because I've taken the viscosity to the left hand side, times y, plus an integration constant c1, and on the right hand side that equals dvx by dy. I can examine the value of that integration constant by looking at my first boundary condition, and I know that due to my axis placement that dvx by dy equals 0 at y equals 0. So therefore my integration constant c1 equals 0. So that's rather useful. Let's now do the second integral. We have on the left hand side delta p over mu L times y integrated with respect to dy is going to be equal to the integral of dvx. So let's take that integration step, and we end up with delta p y squared upon 2 mu L, because we've integrated with respect to dy, plus an integration constant c2 is going to be vx of y. And we can evaluate c2 by means of our second boundary condition. And this is the no-slip boundary condition. Fluid is stuck to the upper wall and the lower wall. And we know that vx is going to be equal to 0 at y equals plus or minus h. Now, it's rather useful that we're dealing with a term in y squared when we implement this boundary condition, because h squared is just h squared, and minus h squared is h squared. So we can set the right-hand side to 0, we can set the left-hand side to delta p over 2 mu l h squared, and that gives us my second integration constant c2 as minus delta p over 2 mu l times h squared. And so the result that we end up with is my x direction velocity, vx, which changes as a function of y, is delta p over 2 mu l y squared minus h squared. So there is my parabolic velocity profile that we started with. So let's recap a few key points. We've solved the Navier-Stokes equations for a pressure-driven flow of a high viscosity fluid in a very small, infinitely wide slot. We applied this four-step protocol to simplify the Navier-Stokes equations, and we carefully placed our axes to allow easy evaluation and incorporation of boundary conditions. We ended up with a flow profile that was parabolic, and this was in a Cartesian coordinate space, and so one of the key learning points here is that in the Cartesian coordinate space, for pressure-driven flow, if the flow is unidirectional, you're going to get a parabolic velocity profile of some sort or other, depending on what the walls are doing. If the walls are stationary, it's purely parabolic. If the walls might be moving, then there will be a parabolic component superposed onto something else. And we'll look at what that something else is in the final part of this lesson.